Welcome to The Explainer. I'm absolutely thrilled to have you here today. We are jumping right into a seriously fascinating journey, taking abstract machine learning math and applying it directly to physical material science. Specifically, we're unpacking sections 4.4 and 4.5 of our source material. We'll be moving from the comfort of idealized linear baselines straight into the heavy-hitting realm of constrained regularization models. So if you've ever wondered how engineers actually predict the strength of a brand new alloy before it's even forged, well, you're in exactly the right place. Let's dive in. All right, here is our roadmap for today. We'll start with the ideal linear baseline, look at the overfitting problem, introduce regularized constraints, compare ridge and lasso budgets, see predicting hardness in action, and finally figure out how to choose the right model.
Okay, Section 1, the ideal linear baseline. So we begin by mapping basic math directly to actual physics. Now you're probably super familiar with the classic linear equation, y equals wx plus b. But in materials science, these letters take on a really deep physical meaning. The output, y, isn't just a number, it's a target material property like yield strength or hardness. The x represents observable physical features. Think stuff like cooling rates or carbon content. The w, or the weights, well, they represent the quantified physical influence of that specific feature. Basically, it's the slope of how much that feature actually matters. And finally, the intercept b is just the baseline property of the material when all those inputs are zero.
Let's see this in action with a simple two-input system. Input 1 is carbon content, which physically represents solid solution strengthening. Input 2 is grain size, relying on the Hall-Petch effect. You know, that core physical principle that smaller grains create stronger metals. We just feed these into a straightforward linear model to get our predicted yield strength.
And the results of this simple model? They're highly predictable. By plotting the experimental data against our predicted data, we get these beautiful, smooth curves. Over on the left, as carbon content increases, the yield strength rises steadily and linearly. On the right, as grain size decreases, the material gets stronger, perfectly following that classic curve. The physics absolutely nail the mathematical prediction here.
When we map the experimental yield strength directly against what our model predicted, the result is honestly phenomenal. In this simple two-variable world, our ordinary linear regression gives us a highly accurate and perfectly interpretable model. I mean, we hit an R-squared of 0.998. That means our model is explaining almost 100% of the variance. Plus, it has a tiny mean squared error of just 9.42. It is literally an engineer's dream scenario.
Which brings us to Section 2, the overfitting problem. Because, as we all know, real life is rarely this tidy. When we scale up from just 2 variables to dozens, that simple, beautiful math starts to break down. Real alloys aren't just carbon and grain size, right? They're this incredibly complex soup of processing temperatures, cooling rates, microstructural phase fractions, and all sorts of trace elements.
And that complexity leads to this messy, chaotic red line. When we introduce dozens of variables, what we call high dimensionality, many of those features end up highly correlated with one another. We call this multicollinearity. And an unconstrained linear model, it just gets completely confused. It has so much mathematical freedom that it violently swings to touch every single data point, drawing this crazy, fluctuating curve. It's overfitting. It has completely stopped learning the underlying physics of the material, and instead it's just memorizing the random noise of the data set. If you tried to predict a new alloy with this red line, no way, your prediction would be completely useless.
Section 3. Introducing regularized constraints.
To save our model from that chaos, we need regularized constraints. Think of it financially, it really helps. Standard regression basically has an infinite black card. Its one and only goal is to minimize error. So it uses infinitely large, wildly fluctuating weights to perfectly fit the training data. And boom, you get the overfitting we just saw. Regularized regression, on the other hand, it's put on a strict budget. It still wants to minimize error, sure, but it's forced to decide which physical features are actually important enough to spend its limited budget on. Notice how this equation formalizes that budget concept. The mathematical objective for our model, which we call J of theta, is now the mean squared error plus a penalty. So to get a good score now, the algorithm has to balance being highly accurate against how heavily it relies on large mathematical weights. It literally forces the model to be elegant and simple. Visually, this mathematical penalty creates these really distinct geometric boundaries that dictate how the model can learn. Check out this regularization topography. On the left, we have a smooth circular boundary. That's the L2 constraint. On the right, we have a sharp cornered boundary shaped like a diamond. That's the L1 constraint.
The actual shape of this penalty boundary changes absolutely everything about what the algorithm is going to conclude about our materials.
Section 4. Ridge versus lasso budgets. Let's look closer at those shapes.
First up is ridge regression, which uses that smooth, circular L2 penalty. Mathematically, it adds the squared value of the weights to the penalty. But practically, because the circle is smooth, the effect is that it shrinks all the parameters smoothly towards zero, but it very rarely zeroes them out completely. For us in material science, the huge advantage here is stability. Ridge is your best friend when dealing with highly correlated processing variables, where all the inputs probably contribute a little bit to the final property, but their combined variance really needs mathematical stabilization.
In stark contrast, we have lasso regression. Lasso uses the absolute value of the weights, creating that sharp L1 diamond geometry. And those sharp corners geometrically demand absolute sparsity. This is a real game changer because it acts as automatic feature selection. Lasso will force the less important parameters completely to zero. This is incredibly powerful when you're mining huge noisy data sets to discover which few specific elements are actually driving the material property, while completely ignoring the rest.
Section 5. Predicting hardness in action.
Let's pit ridge and lasso against each other in a complex, multivariable hardness prediction system. We're looking at 4 variables here: carbon content, grain size, manganese content, and processing temperature. Our goal is to apply both ridge and lasso constraints to this exact same data and evaluate how differently they distribute their predictive weights to calculate hardness.
Take a second to pause here. Ask yourself, if we apply both of these constrained algorithms to the exact same physical data set, what exactly are we expecting to change in the output?
Well, at a macro level, it looks like an absolute tie. On the left, Ridge predicted the hardness beautifully. On the right, Lasso predicted the hardness beautifully. Both models perfectly trace that ideal line, scoring a near-identical R-squared of 0.997. If you only looked at this final prediction, you'd think, oh, these models did the exact same thing.
But wait, here is the dramatic plot twist. They arrived at that highly accurate answer using completely different physical assumptions. Look at this coefficients table. Ridge regression, using its smooth circular boundary, kept all 4 variables in play. It assigned smaller values to carbon and manganese, and larger ones to temperature and grain size. It stabilized the model by shrinking everything. But Lasso? Lasso's diamond corners acted like a scalpel. It determined that temperature and grain size alone were completely sufficient to explain the variance, strictly zeroing out carbon and manganese entirely. It automatically filtered out the noise for us.
Which leads us to our final section, Section 6, Choosing the Right Model.
This brings us to our final rules of thumb, perfectly summarized in this regression diagnostic matrix. Use a standard linear model, only for simple mechanism validation, where the physics are direct and super clear. Step up to the ridge model, with its L2 squared penalty, when you need high stability, like when you have highly correlated ally compositions and you need everything to shrink evenly. And finally, deploy the lasso model, with its L1 absolute penalty, when you're hunting through massive, noisy datasets and you desperately need automatic feature selection to isolate the key processing drivers. Always, always choose the algorithm that matches the physical complexity of your data.
By giving our models strict mathematical budgets, we prevent them from hallucinating on noise, and we force them to find the true underlying physical drivers of material performance. Think about this. As data sets grow to include hundreds of elements and thousands of processing conditions, how might these constrained algorithms like Ridge and Lasso uncover entirely new supermaterials we haven't even dreamed of yet? It's a thrilling frontier. Thank you so much for joining me on this explainer, and keep exploring.